Hi everyone, welcome to AI Crack channel. This is Akash Gangwar, your PGDBA 2026 mentor, and today we will be studying set theory lecture 2. So let's get started with our second lecture on set theory.
So let's try to understand what is a power set. The set of all subsets of a set is called a power set. So let's take a basic example. Let's say we have a set A comma B. We have just two elements A comma B over here. So if we use the formula 2 raised power 2 for calculating the total number of subsets, that comes out to be 4. And those four subsets are, first set is null set, these two single sets, and this one as the improper set. So these are the four subsets of this particular set. Now if we take all these elements and all these sets, we can say, as elements of one particular set, then this becomes a power set. So for A comma B as a set, this is the power set. Basically, a set of all the subsets is called a power set, right? Now let's take an example. Find the number of subsets of power set of 1 comma 2 comma 3. So there are two terms, number of subsets of power set. So first of all, we have three terms in this particular set. We have three terms, we have three elements, right? So basically n equals to 3. So total number of subsets of 1 comma 2 comma 3, that would be 2 raised by 3, that is 8. If you want to write them all, that would be 5, 1, 2, 3, 1 comma 2, 2 comma 3, 3 comma 1, and 1 comma 2 comma 3. So these are the 8 subsets of 1 comma 2 comma 3. Now if we include all these sets or subsets in one single set, that would be the power set of this particular set. So power set will be having 8 elements. So power set, let's say this set is A. So power set of A, and number of elements in power set of A would be having 8 elements. Okay. Now this power set is having 8 elements and we have to find the number of subsets of power set. So in that case, that would be 2 raised power 8. So C is the correct answer. Now let's talk about universal set. A set consisting of all possible elements which occur in the problem or discussion is called the universal set and is denoted by U. That's pretty simple to understand, right? Now there are two conditions for universal set. Sometimes in the problem or discussion, they'll be giving us the universal set. So that is a fairly simple one because they have provided us with the universal set. So we don't have to define by ourselves. Now there's the second case where they'll be giving us sets to operate with. Let's say we have two sets, 1 comma 2 comma 3 comma 4 comma 5, and let's say the other set is 4 comma 5 comma 6. So we have these two sets, we are operating with these two sets in the problem, and now we have to define our universal set by ourselves. In that case, what we'll be doing, we'll be taking all the elements from both the from both the sets, not elements. We'll be taking all the elements from both the sets, considering the property of set that no element should be repeated. So here 4 and 5 is being repeated in both elements. In that case, we'll consider them just once. We'll not be taking writing them in the universal set twice. We'll just writing them once, right? So the universal set in this case would be 1 comma 2 comma 3 comma 4 comma 5 comma 6. So this would be our universal set consisting of all the elements of this set and this set. So in case there is no mentioning about universal set in the problem, we'll define our universal set by ourselves. But in case they have provided us with the set, then it's good. Okay. Now let's talk about Venn diagrams. So before Venn diagrams, we have used roster form and set builder form to represent sets, right? But for visual representation, we'll be using Venn diagrams, and you must have encountered Venn diagrams in your 11th, 12th, or graduation, or post graduation, or during your job as well. So basically, you must have encountered these things, and you know that how easy it becomes to represent sets with the help of Venn diagrams and operations of sets as well. Okay. So just for the sake of defining them, let's see how it looks. So what we do over here, we take universal set as the rectangle, and we take individual sets as the circles. They might or might not intersect. It depends on the question or set. They might or might not intersect depending on that, they have, if they have some common elements or not, right? So it varies from situation to situation and problem to problem. But the thing is, they are being presented by circles. Basically, individual sets are being presented by circles, and universal set is being presented by rectangles. Okay, so this is how we usually define Venn diagrams. Let's try to take one example over it. Let's say we have set A equals to 1 comma 2 3 4 5. Okay, we have set B as 3 comma 5 comma 6 comma 7 comma 8. Okay, so basically we have this rectangle over here, and this rectangle is universal set. So universal set, with the help of our definition, we haven't been provided with universal set in the question, so let's define it by ourselves. So we have 1 comma 2 comma 3 comma 4 comma 5, all the elements covered from A, but we know that 5 is common over here, 3 is common over here, so the remaining elements are 6 7 8, 6 comma 7 comma 8. So this is our universal set. So this entire rectangle is consisting of these elements. Now let's try to define set A and set B with the help of a bubble or circle, right? We know that 3 and 5 is common in both. Let's make it a little like this. So 3 and 5 are presented over here because they are common to both A and B. And 1, 2, 4 is here, and 6, 7, 8 is here. So that gives us the complete presentation of these sets and universal set with the help of Venn diagrams. This entire set is having all these elements. 3 and 5 is common to both. That comes under the intersection area. And 1, 2, 4 is the individual area for A, 6, 7, 8 is the individual area for B, right? Now let's talk about operations on sets, and the first one to be defined over here is union of sets. And you must have heard about it during your college days, right? Or maybe graduation, post graduation, school days, whatever. But let's define it formally once again. Okay. It is being defined by A union B over here, and this symbol is known as union. This symbol looks like upper cup, or it looks like capital U, right? And it actually means X belongs to A or X belongs to B. What do we mean by that theoretically? This is mathematical thing, but what do we mean by in terms of language or crude form, right? So let's take an example. We have A and we have B. A is having 1 comma 2 comma 3 comma 4 comma 5, and B is having, let's say, 4 comma 5 comma 6 comma 7. Now, when we are writing C equals to A union B, in that case, we'll be having 1 comma 2 comma 3 comma 4 comma 5 comma 6 comma 7. Now notice that we have not directly added both of them, because if we have just added, then 4 and 5 would have repeated twice. What we have done, we have omitted 1, 4 and 5 over here and written just 1, 2, 3, 4, 5, 6, 7. Basically maintaining the property of sets, that we are not repeating terms over here. We are not repeating elements inside the set. Every single element is a different element. Okay. So that's why this is how it's A union B is being defined, where we are not repeating terms, but we are including all the terms of A and B. All terms of A are present in there, all terms of B are present in this particular set, but terms are not being repeated, although they are present twice in both A and B. Okay, so this looks like this marked region. This entire marked region is A union B, right? Now let's move on to the second one, that is intersection of sets. And that is defined by down cup or inverted cup, you can say, and inverted capital U, you can also say that. And this looks like this one. Okay, it means X belongs to A and X belongs to B. In this case, it was OR. Basically, it was including all the elements of A and B. But over here, we are including all the elements only which are common to both A and B. Right? Only those elements which are common to both A and B, and not all the elements. So let's take the same example once again. We have 1 comma 2 comma 3 comma 4 comma 5 over here, and B as 1, sorry, 4 comma 5 comma 6 comma 7. So we have 4 comma 5 as common over here. So we know that in case of Venn diagrams, the common elements are being presented in this region. In case they are present, if they are not present, we cannot, we don't have anything over here. They are disjoint sets. Okay, we'll talk about that later. But as of now, we have some common elements over here, and these elements are nothing but 4 comma 5. Okay, so this region, this marked region, is known as intersection. Now the third operation on sets is difference of two sets, that is A minus B. And this one particularly is a little confusing one. So let's try to understand with the help of filtering mechanism. That I personally use to understand or remember this particular definition. Okay. Let's say we have a set A equals to 1 comma 2 comma 3 comma 4 comma 5 comma 6, and we have set B as 3 comma 4 comma 2. Let's say this is the set B, this is set A. Now, what do we mean by filtering mechanism over here? We have to retain all the elements of A which are not present in B. I'll repeat it once again. We have to retain all the in this new set, that is A minus B. We have to retain all the elements of A which are not present in B, right? Basically, we have to let go. We have to filter out all the elements which are present in B. What is present in B? 3, 4, and 2. So we have to let go 2, 3, and 4 from here, and the remaining one, left out one, the one which is being retained, that is C, that is A minus B. I'll repeat it once again. We have to filter out all those elements which are present in B, or in other words, we have to retain all the elements of A which are not present in B. Okay, so this is how we have defined with the help of a filtering mechanism. Okay, now in case of Venn diagrams, this looks like this particular region. So all the elements of A which are not present in B. Okay, this one. Now the fourth one is symmetric difference of two sets, that is A delta B, A minus B union B minus A. So that's pretty simple to understand over there. We saw that A minus B was this one, and B minus A is this one. So union of both of them, basically including all the elements of this one and this one, that gives us the symmetric difference, that is A delta B. Okay. Complement of a set. So this is pretty easier to understand. Let's say this is our set A. This is our set A over here, this circle. So the complement of A would be, this is A. So the complement of A would be the outer region. So you can simply say that this is U minus A. This entire set is the universal set, and we have to subtract the elements of A. Basically, subtracting the elements of A from the universal set gives us the complement of A. Okay. Now talking about disjoint sets, let's say we have two sets A and B, and there is nothing common between A and B. Let's say A is 1 comma 2 comma 3 comma 4, and B is 5 comma 6 comma 7 comma 8. So we can see that there is no common element between A and B. So that means A intersection B is 5. Intersection means all the elements which are common to both A and B, and we don't have any element which is common between both A and B. In that case, that set comes out to be a 5 or a null set. Okay. Now let's look at this example. We have A equals to this, B equals to this. We have to find B minus A minus B. Okay. So let's define A minus B as C. C equals to A minus B. Let's try to define this one first. So we have C equals to A minus B. We have to filter out all those elements from A. We have to retain all the elements of A which are not common in B. So C equals to, is 1 present in B? No. So 1 would be here. If 2 here, yes. So it won't be coming over here. If 3 here, no. So it would be here. If 4 present in B, yes. So that's why it won't be coming. 5 present in B, yes. 8 present in B, yes. So we have got C as 1 comma 3. Now we have to find B minus C. So B is this one, 2 comma 4 comma 5 comma 8. So let's call it as D. This entire set as D. So D equals to, is 2 present in C? No, so 2 would come here. If 4 present in C, no, it would come here. 5 present in C, it would come here. 8 present in C, it would come here. Right? So there is nothing common between B and C. So that's why all the elements are being retained over here. So this is our final answer. Now let's try to solve this particular question. Let A equals to 1, comma 2, comma 3, comma 4. Find the total number of unordered pairs of disjoint subsets of A. So unordered pairs of disjoint. These are the two main keywords of this particular question. Let's try to understand this question with the help of a smaller example of 1, comma 2. Right. Now we have to create unordered pairs of disjoint subsets. So let's start with phi. Corresponding to phi, what can be the other pair of disjoint subset? That would be 1 or 2 or 1 comma 2 or 5 itself, right? So these all are 5. So corresponding to 5, we have these many pairs of disjoint subsets. Now corresponding to 1, now we can have 5 as well. Corresponding to 1, we can have 2 as well. We cannot have 1 comma 2 because that would have 1 as common in both of them. That won't be disjoint. In case of disjoint, we have just two possibilities for 1. Similarly, for 2, we have 1, and for 2, we have 5. These are the only two possibilities. And for 1 comma 2, we have just 5 because both 1 and 2 would be common. One would be having something common between 1 and 2, right? So we have just 5 over here. Now if you look at it closely, you can see that this one and this one is same when we are talking about unordered pairs. When we are talking about unordered pairs, a comma b and b comma a is same. In case of ordered pairs, a comma b comma a are different. But in case of unordered pairs, we are talking about unordered pairs over here, a comma b comma a both are same, right? So 1 comma 2 5 and 5 1 comma 2 both are same. So this is being repeated twice, right? Now similarly, if you look at all other elements except 5 comma 5, every other element is being repeated twice in case of unordered pairs, right? So we'll consider this as 1, and the remaining 8 will be divided by 2, so that would be 4. So total number of unordered pairs would be 4 plus 1, that is 5. So that is the basic idea behind counting all the unordered disjoint subsets of 1 comma 2, right? But we won't be counting for 1 comma 2 comma 3 comma 4 because there would be so many possibilities. So how to do that, let's see. So we have the major set as 1 comma 2 comma 3 comma 4, and we have to create subsets, disjoint unordered subsets. So we'll again use the blank method over here, 1 comma 2 comma 3 comma 4. Okay, now one has either the choice to go over here or choice to go over here, or it can stay here as well. Why? Because let's say none of these elements are going over here, so this set would become 5, and this set also would become 5, and this also creates a pair of disjoint unordered subset, right? So any element over here has three choices, either to stay here or go here or go here, right? Let's take one example. Let's say one is going here, two is going here, three is going here, and four is going here. So this creates 1 comma 4 and 2 comma 3 as the subsets. Now we can see that both of these subsets are actually disjoint because there is nothing in common. What we can understand from this is every single element has three options: to stay here, to go here, or go here. So this one has three options, this one has three options, this one has three options, and this one has three options. Now it comes out to be 3 raised to power 4, that is 81, right? Now we have got the odd number once again. Over here we have got 9, and we know that why it is coming to be odd, because there is one case over here which is 5 comma 5. Similarly over here 5 comma 5 case is there which is not being repeated, right? We saw this in this example that 5 comma 5 is not being repeated, it's just counted once. So over here as well it's just counted once. Every other pair is being counted twice. So out of 81, 80 are being counted twice, and this 5 is being counted just once. So 80 by 2 plus 1. So 80 by 2 plus 1, that would give us as 41 as the correct answer. Okay.
Now let's talk about laws of sets.
Commutative law, which says that A intersection B equals to B intersection A and A union B equals to B union A. So we can take the analogy with the help of numbers. We know that 1 plus 2 equals to 2 plus 1, right? So it's the same thing. The operator is same, just the numbers are shifting over here. Similarly, here sets are shifting, interchanging, but the operator is same over here, and both means the same. So let's take an example of A union B and B union A and try to demonstrate that in the Venn diagram. Okay. When we are plotting A union B, in that case, we'll be marking the A region first, and then we are marking B region. Eventually, we are covering all the elements, right? We're not skipping any element over here, and we are getting this entire region as a result of A union B, right? This is A union B. Basically, A is covered first, all the elements of A are covered first, and then the rest of the elements of B are taken care of. Okay. Now, in case of B union A, we're marking B first. Basically, we're taking all the elements of B first, and after that, we're taking elements of A. And ultimately, again, we are covering the same area. This area we got in A union B, and the same area we are getting in B union A. So that means practically they both are same, right? Regardless which one we choose earlier, B or A, we are going to get the same area, or basically same number of elements and same type of elements. Okay. So you can do the same thing for A intersection B and B intersection A as well, and you'll get the same result. So that is what commutative law is all about. Now the second law is associative law, which is again we can take the analogy with the help of numbers. So important thing to notice over here, the operator is same over here. The operator should be same. We can say that 1 plus 2 plus 3 equals to 1 plus 2 plus 3. It's the same thing, right? But the main thing to notice over here is the operator is same. Similarly, just like 1 plus 2 plus 3, over here operator was same. Similarly over here, this operator should be same. Only in that case we can apply the associative law, not in the other cases. Okay. So if you want to take the example of this one, let's take A intersection B intersection C first. So let's say this is our A, this is our A set, this is B set, this is C set. Now we have to find A intersection B first. So A intersection B is this one, and intersection with C. So the C elements are like this. What we are getting eventually, we are getting this area as the intersection process, right? Now if we talk about A intersection B intersection C, let's do this one. Again, this is A, this is B, and this is C. So we have to do the B intersection C first. So this is our B intersection C, and we have to intersect with A. So this is our A. Eventually, what we are getting? We are getting this particular region, which is same as this region. These two regions are same, right? So no matter how we go, we can start with A intersection B and then intersect with C, and we can start with B intersection C and then we can intersect with A. We are going to get the same result, right? So associative law holds true in this theory. Okay. Now the third law is distributive law. Over here, the operator is changing. You can see that operator is changing over here, right? In this case. So it is A union B intersection C. Again, we can take the analogy with the help of numbers. Let's say we are doing 2 multiplied by 1 plus 3. So what do we do? This multiplication gets distributed on 1 and 3, right? So we get 2 into 1 plus 2 into 3, right? So this middle operator remains the same, and this one gets distributed over the elements. So this is exactly what is happening over here. This union is being distributed onto these sets, right? So A union B intersection this middle operator and A union C, right? So this union is being distributed to elements. So A union B, A union C, A union B, A union C, and in the middle we have the intersection over here, right? We can do the reverse as well. In this case, we have A intersection B union C, right? So this intersection is getting distributed to B and C. So A intersection B, A intersection C, and in the middle we have union because of this one, right? Now let's look at this with the help of Venn diagrams as well. So we have A union B intersection C. Okay. So this is A, B, A, B, C, A, B, C. So firstly, we are doing B intersection C. So for B intersection C, we'll be getting this particular region. And we have to do the union with A. So these are the elements of A. And when we are doing union of B intersection C with A, what we're getting eventually, we're getting this region. This is the region we are getting. And let's do this one now. A union B. A union B is nothing but this entire region. This entire region is A union B. And we have A union C as well. So A union C is this region, right? Now we have to do the intersection of both of them. For intersection, we have to find out the area which is cross-checked, right? With red and blue lines. So what we are getting over here is we are again getting this region only. This is the region we are getting, which is same as this region, right? So no matter how we proceed, if you proceed with this one or if you proceed with this one, we are going to get the same result, right? Now let's talk about De Morgan's law. And there is no analogy with respect to numbers in this case because this is specifically for sets. So what does this say is, suppose we have A union B and we take the complement. So this complement is being distributed over the elements, but this operator is being changing. So similarly, if we do A intersection B complement, we'll be getting A complement union B complement because this operator would change. Okay. You can also do the reverse as well. If something is given in this particular format, you can rewrite this in this particular format. Okay, both ways it's possible. So let's try to prove this with the help of Venn diagrams. So this is our set A, set B, set A, and set B. And let's first do the A union B complement. So we know that A union B is this one, this region. So complement of that would be the external region. That would be this one. Anything outside but inside the universal set. Anything outside A union B but inside universal set is the complement of A union B, right? This region. Now let's try to do that with the help of A complement intersection B complement. So for A complement, this is our A region. So what would be complement of A? That would be anything external to A, anything, including elements of B as well. Anything external to A but inside universal set. That would be A complement, right? So this entire region is A complement. Similarly, if we want to plot B complement, in that case, what we'll be getting? We'll be getting anything which is external to B. That would be B complement. Now we have to take the intersection of A complement and B complement. In that case, we have to see this region which is having cross-check lines, right? And this is exactly the reason which we have got over here. This external region over here and this checked region over here is exactly the same. So that is how we can prove the De Morgan's law with the help of set Venn diagrams. Okay. Now let us talk about identity law. So that says A intersection universal set is A and A union null set is A, right? So this entire region is our universal set. And if we are doing intersection with universal set of this particular set, eventually what we are getting this particular set only, right? The cross check lines are over here only, so those are the elements of A only. So we are getting A intersection universal set as A only. And similarly you can prove this as well. A union phi equals to A. Basically we have nothing over here, there is no element over here, and we are doing the union, and we know that A union something is this, right? But this is having no element, so all we have is elements of A only. So A union phi is nothing but A. Now let's talk about complement law. So that says that A union A complement is universal set, A intersection A complement is phi, and A complement complement is A only. That is kind of very obvious. We won't be proving that, but let's look at these two. So we have A union A complement. So we know that this region is A, and the external region, entire external region is A complement. So if we take the union of both of them, basically this region and this region, in that case we are definitely going to get a universal set, right? Because we are covering all the elements of universal set. Similarly, we have A intersection A complement. So we have A as this one, and the external region is this one. We can clearly see that there is nothing in common between both of them. That's why they're complementary. We have nothing in common between these two regions, and that's why it comes out to be null set. Okay. Now let's talk about idempotent law that says A intersection A equals to A and A union A equals to A. That is again kind of very obvious, right? So we are intersecting elements of A with A only. So we are getting these elements only. In that case, we are going to get A only. Similarly, with A union A, we are taking all the elements of A, and not considering the elements which are being repeated over here. So eventually, we are going to get A only. So that is kind of obvious. Now let's look at this question. If A and B are two sets and A dash and B dash denotes complement of A and B respectively, then A union B intersection B dash equals. So now these are the kind of questions you can expect in PGDBA, and they become a little lengthier if you solve them with the help of Venn diagrams. So let's try to solve them with the help of properties. We can see that we have an operator change over here, we have union over here, we have intersection over here. So we'll be using distributive property. Okay. So we have A union B intersection B dash. Now what will happen? This intersection will distribute over these two elements. So this would become A intersection B dash union B intersection B dash, right? Now we know that B intersection B dash is nothing but phi, null set. So this becomes A intersection B dash union phi. And we know that anything union with phi is nothing but this element only, that element only. So that would become A intersection B dash. Now we have simplified this inside bracket. Let's try to solve it further. That becomes A dash union A intersection B dash. Again, we can see that there is a change of operator over here, so we can use the distributive property. So that would become A dash union A intersection A dash union B dash, right? Now A dash union A is nothing but universal set, right? Intersection with A dash B dash union B dash. Now we can write this as A intersection B dash, right? With the help of De Morgan's law. Now we know that anything intersecting with universal set, that would be that set only, right? So this would give me A intersection B dash. So C is the correct answer. So this lecture was still here only, and this marks the end of set theory. So from the next lecture, we'll be starting with relations and functions. So let's meet in the next lecture. Thanks for watching.